Hello everyone. Today we're going to talk about the continuity equation. The continuity equation describes how things behave in space and not only in time like we've done so far, and we will see how we combine things later on together. So to start with, we have to consider a vector field. So a vector field I can just draw as a bunch of arrows, which are really going to be the vector field. So you can think about vectors in space, and the vector represents flux. Flux means it's how much of a certain fluid, for example, or particles cross a particular interface. So you can think about it that if I have an interface here, for example, and there is a flux that goes in this direction over here, then if I ask me how much of this is crossing the interface, you of course have to look at the normal to that particular surface and see the component in that normal direction, and that you can just compute the amount of flux that goes in. So if you think about the flux vector as a vector j, as a vector here like this, the amount that crosses the interface locally, at least at one point, will be j that is normal, so dot n, where n is the normal to the surface, and that would be the amount of flux that cross any particular surface. So the goal of what we're doing when we're thinking about fluxes and about surfaces in a second will be to look at how the flux looks with volumes, and how do things change in a particular volume. And that's what we're going to be doing. So in the next question we have, assuming we have some flux field, and we have a particular volume over here, doesn't matter which volume we have here, we can ask ourselves, what is the change of mass in this volume as we go in time, so in a unit time. So if I think about it, what I'm asking to know is, how is the change of mass, dm, change over dt in that volume? And that's actually, with you thinking about flux, it's a rather simple question to answer. You can think about the flux that comes into this whole thing. So this will be flux that comes in, a flux that comes in, and a flux that comes in, and maybe a flux that comes out. So flux that comes out would be something like this. And if you think about the change of volume, it will be very simple. It will be whatever comes out, whatever comes in. So I can think about it this way. If I go ahead and I integrate over j, which is my flux, dot n, which is the normal of the surface. If I look at every point here, it will give me how much flux coming either in or out. Remember that the normal is always defined in a certain direction, so I would just have flux coming in the right place, flux coming out in that place. And if I integrate this whole thing over the area, so over the surface in this case, the S of that particular thing, over the whole surface, that will give me basically the change of dm to dt. So the mdt, the change of mass as in the unit time that I'm taking here, will be basically equal to the integral of the flux that coming out minus the flux that coming in, which I can just write as j dot n dot ds, where j dot n basically takes the flux only in the direction that comes in or out of the surface, and multiplies by the small infinitesimal surface volume that exists around here. So that's what I have so far with mass. The thing is that, of course, this is nothing to do with the size of the volume. The volume can be bigger, can be smaller, and I want to normalize it. So one of the ways to normalize it is just say, okay, if I just divide it by 1 over the volume over here and 1 over the volume over here, then I'm going to be normalizing it by the volume, and now everything is not volume independent. And that's the first thing I can do. The second thing I can do is to take the volume and make it smaller and smaller and smaller until it becomes infinitesimal. And mass divided by volume is giving me the density. So now I can think about this as the change, and I'm going to move to partial derivative in a second, to density as a change in time. That's going to be equal to the 1 over the volume. Now I still have the volume that it still has here, times the integral over the surface still here of j dot n ds, and so far this is individual to the size of the volume that I have here. Last thing I want to do with this particular thing is, again, to see what happens as the volume now shrinks to 0. So I can shrink the volume to 0, and that give me a definition. So if I go ahead and shrink the volume to 0, let me just go to drawing again. I can define the following thing. I can define that the divergence operator of a flux J is equal to the limit as the volume goes to 0 of 1 over the volume, the integral over the surface of J dot N dot ds. There is a dot here. The importance of this thing is, if you think about the definition, is that this definition is very straightforward. What it implies is that the change of the density that is going to happen in is just going to happen depending on the stuff that comes in and stuff that comes out. So the divergence operator is a very simple operator. The divergence operator, it says whatever comes out minus whatever comes in is giving you the change. So it looks very complicated in the beginning when you think about it, but if you think about the picture on the top, it's a very simplistic evaluation of what the divergence. This picture at the top should be the picture of divergence. Divergence is whatever comes out minus whatever comes in, and that's going to give you the change of things. Now, for example, if we have fluids that are incompressible, every volume that you have you can never have something comes in and not coming out because it's not compressible. In that case, the divergence of fluids that are incompressible is always 0. In earth science, most of the fields we deal with are incompressible, and the divergence is 0. For example, water is clearly the case. The compressibility is extremely small. Even air, when you look at it in the atmosphere and you consider how much it's actually condensed and what in the pressures we are usually facing, you'll find out that it behaves almost as an incompressible fluid. So in the earth science, in many times, we're thinking about incompressible flows. However, there are cases that we will consider to be completely compressible. For example, we just talked about modeling of diseases, and until now, the disease was only in time. But you can think about two compartments. So you can have this compartment, let's say here would be North America, and this compartment here will be China, and the flux will be the stuff that comes out from China and goes to the US or to Canada. And you can think that, for example, you're going to have more patients here in this volume over here than in this, and of course they can go back and forth, and the flux that can go in can just compress more people in and compress more people out, and you can think about it as a compressible fluid. And we will see that these kind of things can be used in order to model different types